is not able to present and be here with us today, but it's a great pleasure for me to take this role from him and to introduce to you Francesca Chelazzi. This is the introduction has been prepared by Thanasis, whom I would like to thank. So, dear colleagues, ladies and gentlemen, good evening and welcome to the 9th lecture of the 59th public lecture series of the Archaeological Research Unit of the University of Cyprus, titled Traveling Archaeologies. It is my pleasure to introduce our today's speaker, Dr. Francesca Chelazzi, Research Associate and GIS Specialist at the Department of Archaeology of Durham University, in the framework of the ERC project coordinated by Dan Lawrence, Climate, Landscape, Settlement, and Society, Exploring Human-Environment Interaction in the Ancient Near East. Francesca Chelazzi studied archaeology at the University of Florence and pursued her postgraduate studies at the same institution, graduating in 2007, and at the University of Siena in 2008. Dr. Chelazzi undertook her PhD research at the University of Glasgow under the supervision of Claudia Glatz and Michael Given, and I see Michael is in the audience, so hi Michael, and was awarded her doctoral title in landscape archaeology with the thesis Landscape Strategies in Bronze Age Southwestern Cyprus in 2016. Francesca has been a very active researcher since very early. In 2009 to 2010, she worked on a Bronze Age ceramic analysis from the Kouris Valley with a fellowship from the University of Turin. In 2011 to 2013, with another fellowship from the same institution, to work on artifacts and landscapes from Erimi. In 2018, on community heritage in the Adelphi Forest in Cyprus with Erin Gibson from the University of Glasgow, and in 2019, on the Roman landscapes of Greece with Emery Farinetti from Roma 3. Our today's speaker has also taught GIS and spatial analysis, remote sensing as a lecturer and teaching fellow at different academic institutions, namely at the University of Chieti and Pescara and at Roma 3. Francesca worked also as a postdoctoral researcher at the University of Chieti and Pescara in 2021, and then in 2022 at the Archaeological Research Unit of the University of Cyprus, in the framework of the Interreg project, Metal Places, Cultural Crossroads in the Eastern Mediterranean, coordinated by Vasiliki Kasianidou and supervised by Apostolos Saris. Dr. Chelazzi has participated in numerous field projects since 2002 at Kaulon in Italy and at the Kouris Valley in Cyprus, with the University of Florence, at Lofu with the Museum of Limassol, at Moni Pyrgos with the University of Chieti and Pescara, in Asgata and Kalabassos with the University of Cyprus, and at Sirwan in Iraq with the University of Glasgow. Francesca has published more than 20 scientific papers in peer-reviewed journals, edited volumes and conference proceedings on land use patterns, the interaction, human environment and climate interaction, mobility, consumption, and the material culture of prehistoric and protohistoric Cyprus, the Eastern Mediterranean, and the Near East. She is currently co-editing the volume, the Sirwan Regional Project 2013-2022, to be published with Sidestone Press. Closing this introduction, I would like to kindly ask all our participants to keep their cameras off and their microphones muted. Should you wish to address a question or comment to our speaker, feel free to use the chat button on Zoom. But please, this is my parenthesis, do so after the lecture is finished, because if you do it now, it pops up during the presentation and it disrupts the speaker. You may also switch on your cameras after the end of the presentation to address your question directly to the speaker by raising your hand and unmuting your microphone. Before I say, I would like to say that was the introduction by Thanasis. I would like to say that Francesca has been a valuable member of the Archaeological Research Unit and our research team on the Metal Places project. She has worked very hard in the lab and in the field. She has the energy of 10 persons at the same time. And I would like to thank her publicly here for all she has done for the project and all she's still doing. I mean, although she's now no longer formally a member of the team since she has moved on to Durham, and they're very lucky to have her there. She still works with us, and she will help to finish this very important project. And I would like to publicly thank her for all the work she has already done. It has been a pleasure to work with Francesca. Now I give her the floor and to present this very interesting lecture with the title, Everything in Nature Invites Us Constantly to Be What We Are, Exploring the Evolution of Humans and Natural Communities in Ancient Cyprus via Multi-Proxy Analysis. So Francesca, the floor is yours. We look forward to listening to your lecture.
Thank you so much, Lena, for this exceptional welcome. And I'm speechless and I'm getting a little bit emotional. So I would like to thank you, to thank Apostolos Saris, to thank my former colleagues, Sabina, Andreas, Dimitris, as well as Dora, Artemis, Anna, everyone based in Gladstone Street. I had a very incredible period of my life there, professionally speaking, personally speaking. So I'm really so happy to be here, and I'm also honored to speak today about the interaction of people and their environment in Cyprus during the Holocene period. So let me share my screen, one of the many screens I have on my desk right now. Hope you can see the full screen.
Yes, everything is fine. Thank you very much.
Okay, brilliant, better than expected. So I selected for my presentation a title that starts with a quotation that isn't mine, but comes from Gretel Ehrlich, an American travel writer and a novelist, because I think that it captures a lot of the debate about humans and the environment and how they interact with one another. And I like how she uses the word nature because it encompasses not only the physical environment, but also the biological processes, the natural reactions to changes, the drivers, the outcomes. Nature, of course, includes also human societies, which are referred to here as biota entities, as organisms that act in a certain way, more than one way, and take actions that have causes and effects. Someone might argue that this quote is a little bit too environmentally deterministic, and I agree. As a result, before we get into the game and the graphs, let me clarify a few things. The first point is that I added vice versa at the end of the quotation because the goal of my talk today is to map the constant interaction between humans and environmental communities while keeping in mind that what's really interesting in this story is more cultural than environmental. It's the mechanism of this interaction, the tempo, the rhythm, the place, the notes, the patterns. The term evolution in my title might raise a second criticism, but please don't just look at this term from a strictly evolutionary and Darwinian perspective. In the next 40-55 minutes, I'll be using this word frequently. So I'd like to think of it as a synonym of trajectories, dynamic interactions, processes of trial, error, good ideas, terrible results, and so on. But I've always found it fascinating to consider background concepts like coevolution, which was first proposed by Richard Norgaard, professor of ecological economics at Berkeley, who defined coevolution as, quote, the sum of evolutionary changes of interrelated entities selecting on the characteristics of each other. And I think that there's not that much Darwinian undercurrent in these words, which talk of comprehending the reciprocal process of change between population and the environment. And these patterns of interactions are historically contingent because they're the product of interactions between social organization, technology, values, knowledge, and the environment. This feedback system is also embedded in another concept, conviviality, by Austrian philosopher Ivan Illich, who spoke about, quote, the autonomous and creative intercourse among persons, as well as the intercourse of persons with the environment. And this concept is especially important because it focuses on one key point. We have the humans, we have the environment, but we have also other humans who interact with us, and through this interaction, which could be economic, social, political, cultural, symbolic, cognitive, or even spiritual, they may leave signs on the environment. In any case, the body of literature, theories, models is enormous, and it covers anthropology, biology, economics, ecology, philosophy, every field, and both the natural and social sciences, including, of course, also archaeology. My goal today is not to engage in a theoretical debate about the more biological or even philosophical aspects of humans-environment interaction, but rather to focus on a few methodological aspects and techniques for investigating this subject using archaeological data. In the next 40 to 55 minutes, I'd like to focus on a few points, including why archaeology matters when considering patterns of interactions between people, the environment, but also climate conditions, what we need to investigate this subject in archaeological research, including the datasets we need and those we already have, and the tools for combining knowledge and analyzing patterns. And I will then focus on Cyprus and its legacy data, and I'll show you the preliminary results of a few multi-proxy analysis techniques. So let me start from the very first point, why archaeology matters. First and foremost, it matters because it's not our view as archaeologists. The Intergovernmental Panel on Climate Change, IPCC, is the United Nations body in charge of assessing the scientific basis of climate change, its effect and potential risks, as well as adaptation and mitigation options. Since 1988, the IPCC has published reports that have been critical input into international climate change negotiation. Every IPCC report stresses the importance of understanding past climate change and human responses in order to develop a more sustainable policy plan in the coming years. This summary table shows, the IPCC believes that understanding previous interactions is critical at all the spatial scales, from the global to the village. According to the IPCC, this is especially important in the case of small islands that are particularly vulnerable environments because of the diversity of their physical and human characteristics, as well as their responses to climate-related drivers. Adaptation was, is, and probably will be variable from one island to the next. The IPCC contends that this diversity of potential responses, including the past histories, has not always been properly integrated into adaptation planning. However, as archaeologists, we are aware that our work is relevant to the modern world, especially at this historical juncture where climate change is a source of concern for different generations as well as policymakers. In the spring of 2012, a web-based survey was launched across North America and Europe's archaeological communities with the goal of finding, quote, problems of broad scientific and social interest that could drive cutting-edge research in archaeology for the next decade and beyond. This survey produced a list of issues, themes of global significance, addressing historical processes working at various spatial and temporal scales, from households to empires, from hybrid climate changes to long-term land use transformation. And surprisingly, many of these themes revolve around finding, exploring past patterns of human-environment interaction, resilience, collapse, spatial and material reconfiguration of past landscapes. Archaeology is well suited to do so for a variety of reasons, including its multidisciplinary nature, its ability to generate and analyze new data to answer these questions, its suitability for working at different scale, and its track record of borrowing analytical tools from other disciplines and adapting them to our needs. But above all, archaeology has collected an impressive amount of legacy data in the last century.
Francesca, may I ask you to maybe move your microphone a little bit because there's some okay, let's try. There's some
Hopefully,
noise. Okay.
Hope it's better. Okay.
Better.
As a result of this new wave, in the last 5 years, new intersectoral academic projects have been commenced to synthesize the various sources of information at our disposal, as well as the numerous proxies, and co-analyze them in order to investigate the feedback mechanism between humans and the environment. Two important examples of this new wave are the changing face of the Mediterranean, led by the University College of London, and the CLASS project by Durham University that focuses on the Fertile Crescents but also expands across other regions of Southwestern Asia for specific research teams. So how these projects operate, what kind of data we need, what kind of analytical tool. So let's start from the datasets. 3 different types of archival data are usually the foundation for this kind of study. Archaeodemographic proxies are typically settlement data, surveys, and radiocarbon dates that are analyzed and modeled using various statistical methods to infer evolving population patterns over time. Archaeobotanical and zooarchaeological data by archaeological proxies can help identify subsistences regimes, the seasonality of farming, herding, hunting, animal killing habits, and the intensification or extensification of agrarian activities. Several types of examined contexts, such as lake sediments, speleothems, ice core, tree rings, insects, are used as paleoclimatic proxies. In addition to the usual measure oxygen and carbon isotopic data, the most recent speleothem data also includes trace element ratios, strontium-calcium, magnesium-calcium, for example, which are especially sensitive to aridity. Archaeodemographic proxies are a widely diverse dataset, and it's difficult to generalize because survey project density, coverage, methodologies, even theoretical frameworks vary by region and by time. We have a wide range of resources at our disposal, from published papers and monographs, which are typically the primary source for obtaining site-based information, to online repositories such as FASTI Online. Another important legacy source for population dynamic modeling is radiocarbon dates. Users can easily obtain tabular data from online repositories like Radon, Oxcal, and others, and then harmonize and process them using several statistical techniques. Many online infrastructure can retrieve bioarchaeological proxies, including ADEMNES, the archaeobotanical database of Eastern Mediterranean and Near Eastern sites, which includes many Cypriot sites, their vegetational profile, and information about animal bones. Other sources include publications that have already compiled the various datasets and made the spreadsheet accessible on the internet. Finally, paleoclimatic proxies are stored on multiple platforms, including the National Oceanic and Atmospheric Administration and the PAGES Network Speleothem Isotope Synthesis and Analysis Working Group database. These online platforms enable for the download of raw files and raw isotopic data in TXT format, which can be easily processed statistically. And this brings me to the second point. What are the analytical tools we use in multi-proxy studies? Population proxy survey data and radiocarbon dates are generally analyzed through a complex set of statistical techniques, including raw count of sites, which is literally the raw site frequency of data, total area, which is an estimation of the settlement area in use in a period, aggregating the individual size of each site using specific time slices, usually 200 years. Heuristic weight is another technique borrowed from criminology, and it determines the probability for the contemporaneity of crimes, in our case, sites, and then randomize start date, which models the start dates of sites using randomization, typically 1,000 randomized runs, and then bins the results into time slices, usually 200 years. All these methods use the input of settlement data, survey data. The final technique, the sum probability distribution of radiocarbon dates, is a little bit different. And it's rooted in the assumption that the more people live in a given region, the more garbage, the more organic material, the more radiocarbon collected and dated. This method essentially employs a probabilistic density approach to estimate the chronological distribution of the dated items. It was developed in the late 80s and has been recently revived and further developed as part of the UCL project, The Changing Face of the Mediterranean. Of course, some criticism is being leveled at this specific technique, especially the use of radiocarbon dates as data and as proxies for even counting points-wise comparisons, because SPD, some probability distribution, conflates the density of our dates with uncertainty about their temporal position. Nevertheless, SPD analysis is widely used as a proxy to investigate population trends in conjunction with the other techniques and the other proxies. The final results of population modeling looks like this, with several distinct lines showing the patterns as processed by the various algorithms and the chronological scale on the x-axis, usually expressed in years BP instead of BC to avoid problems with negative numbers during the computation. The top graph, this one, depicts the sum probability distribution, with the gray shaded region representing a critical Monte Carlo envelope encompassing the middle 95% of the simulated distribution, and the red and blue lines, areas, highlighting portions of the curves where positive and negative deviations are detected. These population models patterns can be compared to other data sets, specifically bioarchaeological proxies, that can be used to identify regional scale vegetation patterns throughout the Holocene. Using a cluster analysis-based method, is it possible to determine the major vegetation type that include both forest, woodland, and open or shrubland vegetation types from fossil pollen record, cores, and pollen surface samples? These samples are usually taxonomically harmonized, and the pollen count data are summed into time windows, again, usually 200 years. The final graphs show the percentage of pollen samples statistically assigned to each cluster group over the course of the Holocene, and the y-axis represents time. These patterns can be further processed to produce pollen infer indicator groups like arboreal pollens, cultivated trees like olive, walnut, chestnut, pastoral land use indicators, several groups that we can take into account when we think about human activities in the landscape. The evolution of these indicator groups over time can be easily correlated with the archaeodemographic proxies to map possible correlations and compare the historical development of these groups with archaeodemographic modeling. And in addition, these trends can be plotted against paleoclimatic proxies to determine whether climatic conditions played a part in this game. Additionally, finally, paleoclimatic proxies can be directly mapped onto archaeodemographic proxies or used to create new models in the area of climate studies. This is an example of a pretty recently published model developed as part of the CLASS project here in Durham. So let's finally talk about Cyprus. What kind of proxy data do we have from the island? What knowledge can we glean from their integration? And how can we play with these data sets? Let's start with demographic proxies. The settlement data from the vast majority of the survey projects that have been conducted on the island over the last 50 years was recently reviewed and compiled for this very important paper, which was published on the Journal of Open Archaeology last year. Although we know that survey data are affected by some biases and uncertainties in terms of coverage, density, even theoretical background, this catalog compiled by Catherine Crawford and Marc-Antoine Vella is a very precious source of information, as it includes more than 8,000 site phases from the island from 1,500 sites. A second equally significant data set is this one, which is the biggest collection of uncalibrated radiocarbon dates for the entire Near East, and was published in 2012-22 by Palmisano, Bevand, Lawrence, and Shannon, again a contribution by the CLASS project here in Durham. It is made up of over 11,000 dates from 1,000 sites, and Cyprus is represented by 54 sites for a total of 493 dates. So this is the result of the various analytical techniques I described earlier being applied to these datasets. The x-axis represents time in years before present, but here you can see the chronological subdivision of, this part of the Holocene according to the main cultural phases. Although settlement data are pretty nicely correlated, of course, because they're based on the same data sets among each other, the correlation with SPD values results pretty questionable, and the Pearson's correlation table demonstrates these points. The primary argument is that when compared to settlement data, SPD usually overestimates population density during the earliest periods of the Holocene. This is unquestionably because when working with sites when there's no pottery at all, or where our understanding of pottery sequences is pretty fragile, archaeologists rely particularly on radiocarbon dating techniques. The contrary argument applies to the classical and post-classical periods because archaeologists generally use typochronologies to date material culture. But because we don't have enough radiocarbon dates to analyze, the SPD pattern is broken. It terminates at the end of the late Bronze Age. So the demographic distribution, our population pattern is pretty interesting. According to these different patterns, the late Epipaleolithic and Aceramic Neolithic periods in Cyprus are characterized by two distinct stories. The SPD, which is the orange line, shows several episodes of demographic growth that might relate to the repeated arrival of newcomers during the PPNA and the PPNB, but may also be, and probably it is, the result of the impressive number of radiocarbon dates we have from this specific time period. Nevertheless, a population growth is suggested also by the other proxies, and it is particularly pronounced at the end of the Aceramic Neolithic. Regarding to the so-called 8.2 KBP event, the SPD trend is interesting. Stable oxygen isotopes from Jaita Cave, Jerusalem West Cave, and Sore Cave in the Levantine region show that this period was characterized by aridity and decline in temperature, but we'll see this in a minute. The early ceramic Neolithic contains several negative deviations from the archodemographic trend, which appears to be characterized by a general decrease in the size of Cypriot population. While the other proxies indicate a slightly growing population throughout the entire ceramic Neolithic, the SPD trend line peaks at the end of this period in the second half of the 8th millennium BP. The Chalcolithic period is characterized by an expanding population, particularly during the late Chalcolithic, and this is indicated by all the population proxies analyzed. Paleoclimatic proxies, especially the Jaita cave, indicate that the end of the 7th millennium BP and part of the 6th millennium BP were marked by a persistently arid climate, punctuated even by drier episodes. In this regard, the comparatively modest increase during the 6th millennium BP and a possible decrease at the end of the same millennium could be explained by a potentially temporal demographic decline that scholars have related with the phase of agricultural de-intensification, but I'll return on this point in the following slides. Crop cultivation and caprine husbandry expanded in tandem with population development beginning in the late Chalcolithic. It is doubtful whether there was a demographic decline in the second half of the 5th millennium BP, which corresponds with the so-called 4.2K BP event. But I'll show you the local climatic conditions we can deduce from Cypriot paleoclimatic proxies in the following slides. However, it's important to remember that this period, which mainly correspond to the transition Filia Early Bronze Age, is quite complex, not only in a strictly historical sense, but also for our capacity to identify surface ceramics dated to the Filia period. And this is particularly crucial when dealing with legacy data. The Bronze Age was marked by a general increase in population. Each population proxy suggests a different time frame for this process, but in general, our settlement data indicate that population grew significantly during the 2nd millennium BC. The end of the Late Bronze Age coincides with the end of our SPD model, but the other proxies also indicate a general demographic contraction. The number of sites increased again during the Iron Age before peaking during the Archaic period and then declining during the early Classical period. Finally, during the early Roman period, there was another period of demographic growth, followed by a phase of slow population decline starting in the late Roman period. But obviously, more factors must be considered, including the attention given by survey projects to identify Byzantine, French, Venetian, and Ottoman material culture. Another bias is the uneven spatial distribution of our radiocarbon dates as well as our settlement data. As we know, and Cyprus is a good illustration of this, certain projects were primarily focused on certain periods, where other projects were focused on other periods in different regions. Despite the fact that both mapped as many locations, as many sites they could find, they both probably had some bias. As you might expect, the vast majority of our radiocarbon dates from the Chalcolithic period come from the southwest of the island. And you can see the cluster of dates, those very reddish area in the regions of Kisonerga and Lemba, while radiocarbon dates mainly come in terms of the ceramic Neolithic from the southeast. The cluster at Paraclesia, Aios Dichonas, Chirokithia, as well as a great quantity of radiocarbon dates from the late Bronze Age site of Kalavassos, Aios Dimitrios. This, of course, has an impact in terms also of the spatial component of our models. Determine the scales of analysis to apply when we tackle to the geographical scale problem is yet another issue. Over time, numerous topographical subdivisions have been used as analytical units. This is a brief catalog from Myers and Onefash Richter. Oh, I'm so sorry. Okay, from Myers, Onefash Richter to the last subdivision by Georgiou in 2006. What do we mean by regionalism is another more cultural question that David Frankel pointedly raised in 2009. In particular, Georgios Georgiou explored the demography of Cyprus from the late Chalcolithic to the protohistoric Bronze Age for his PhD research at the University of Cyprus, and he subdivided the island of Cyprus into 11 regions. He emphasized that various demographic trajectories were taking on the island, each marked by a distinct timing of population growth, ranging from regions of notable growth like the north and the southeast to regions of minor growth like the west and the northeast. However, although variations in size and timing can be identified, he found the general rise in population in all the regions. What kind of picture can we grow using a regional strategy to geographically subdivide our population proxies? To have a minimum number of sites per region, especially in terms of radiocarbon dates, I've used a simplified version of Georgiou's subdivision. And I have also reprocessed settlement data and radiocarbon dates, grouping them by areas: the southwest, southeast, the Troodos, the Mesoauria, and the north coast. These are the various population stories that we can find. A few differences are evident, including the clustering of Chalcolithic sites in the southwest, but also the north, the different patterns of population growth during the Bronze Age, more pronounced in the southeast, the Mesoauria, and the north, and the different impact of the late Bronze Age crisis, particularly strong in the southwest and the Mesoauria, the possible minor significance of the Mesoauria during the Iron Age and the opposite pattern in the southwest, and a general decline at the end of the Archaic period in the Mesoauria, the Troodos region, and the southeast. How about our biological proxies? So these maps shows the distribution of the archaeological and zooarchaeological data sets from the island, and it's based on this paper by Lucas and Fuller, published in 2020, which is a sort of synthesis of the bioarchaeological data from the ceramic Neolithic to the late Bronze Age. Some interesting points emerges when we compare our population proxies with the characteristic and distribution of the archaeobotanical and zooarchaeological proxies. Let's begin with zooarchaeological data. Each one of these points represents the relative frequency of animal bones per site. The x-axis indicates time, again years BP, and each site is dated according to the median calibrated date. The y-axis indicates the relative contribution to the meat supply. Archaeobotanical data are presented similarly as a sum frequency distribution. Cash crops, vitis and olives, as well as cereals, pulses, and fruits are individually plotted. The ceramic Neolithic is characterized by the arrival of various communities on the island, which gradually introduce various animals and botanical species. During the PPNA and PPMB, they introduced not only Dama mesopotamica, but also sheep, goat, and cattle in small quantities that lasted only a brief time. In terms of botanical species, they introduced wild acorn and emmer-wheat, while the only one believed to be indigenous to Cyprus is wild barley. During the this time, most Cypriot communities relied on a mixed subsistence. Dama Mesopotamica accounts for more than 70% of the meat supply at almost all the sites, together with pig and a small contribution from caprines. Although Paul Croft argued that sometimes some sites, such as Kirokitia and Tenta, were probably too big in terms of population to depend exclusively on deer hunting. The question of whether caprines and pigs were introduced to the island as wild or domesticated animals remains unresolved in this moment. But however, the excavators of Shillurocambos, for example, believe that goat was probably also hunted in this period. Cereals were also grown, and the PPNB period shows a growing amount of pulses and fruits, implying a small-scale intensive garden cultivation combined with hunting and probably even intensive livestock herding. During the ceramic Neolithic, Dama Mesopotamica was still the main contributor to the diet of local communities. In the same period, herding probably increased as caprines and pig got progressively domesticated. Caprines in particular show a slightly increase in the quantity at the end of this period. Antemortem products, milk and wool, for example, do not appear to have been played a relevant role. It has been suggested that this period coincides with the general de-intensification of a local economy. In their 2020 paper, Lucas and Fuller largely investigate and debate on the term de-intensification, arguing that the decrease in the quantity of recovered cereals was, however, coupled with an increase in the recovered pulses and fruit seeds. And they propose a pattern of crop diversification rather than any form of the intensification of agriculture. And this pattern fits well within a general demographic pattern characterized by a low population pressures. Most of the sites were abandoned around 6000 BP, and new settlements were built in formerly uninhabited regions, potentially as a result even of seasonal economies. However, the Chalcolithic period is distinguished by a notable shift in the subsistence economy, which also coincides with a significant rise in population. Hunting remained a significant contributor to the local economy, but beginning in the Middle Chalcolithic period, we see an overall decline in this activity and a steady rise in caprine population. Parallel to this, every cultivar appears more frequently in the set of the recovered taxa. This raises questions about the seasonality of deer hunting and the likely need for a more integrated farming system. Frankel, Webb, and Pictet contended that hunting deer, but possibly also caprines, was likely practices from the end of winter to the end of summer based on the record from the hunting campsite of Politico Kokkinorotsos. This period, end of winter, end of summer, corresponds with the flowering time of the arable weeds that have been found associated with cereals at the main ceramic Neolithic sites. But from the Chalcolithic period onwards, the arable weeds recovered point to a late summer flowering phase. And this might suggest an attempt to schedule labor and probably also to balance deer hunting with raising agricultural reliance that resulted from population growth and probably new patterns of urbanization. Nevertheless, local communities continued to depend on a mixed subsistence approach throughout the Chalcolithic period, which probably also served as an effective risk management strategy in the face of potential droughts. And this pattern, which characterizes the late Neolithic and early Middle Chalcolithic, fits in well within the global climatic scenario of the long fourth millennium to quote the title of a paper by Joe Clark and colleagues, which indicates that from 6.5 kbp to the end of the 4th millennium BC, the climate across the entire Near East and Eastern Mediterranean shifted towards more arid conditions, with an increase in the arid episodes at around 6.4 kbp and some amelioration from 5.1 kbp from the Middle Chalcolithic. The human societies of the Eastern Mediterranean and the Near East were affected by these arid conditions in different ways, depending on the local environment as well as the different subsistence economies. From this perspective, Cyprus did reasonably well during this time, despite a drop in the number of sites at the end of the 6th millennium BP. The late Chalcolithic period, which is characterized by a new population boom, growth, and the growth of settlements, expansion of settlements in previously uninhabited regions, showed an increasing reliance on cereal-based agriculture, presumably along with the expansion of agricultural areas, which reflects again an increasing population. Extensification most likely continued during the early Bronze Age, in parallel with the demographic growth, thanks to the reintroduction of cattle, which helped agriculture spread further to regions with poorer soils and less rainfall. Based on residue analysis and the study of cutting profile, it is possible to put aside a growing demand also for antemortem products, secondary products, during this time, although it doesn't appear that milk and similar products were used as a main resource. Additionally, stable isotope studies of human bones show that the transition from the late Chalcolithic to the Bronze Age was also marked by a shift in nitrogen ratios. While the Chalcolithic patterns were characterized by higher nitrogen values that indicate a diet primarily based on legumes or animals' meat where animals were given legumes, the Bronze Age is distinguished by a general lower nitrogen ratio, which denotes an increasing amount of milk into the local diet. Although cattle aren't mentioned in the summary tables by Lucas and Fuller, it appears probably that cattle weren't the main source of meat during the Bronze Age. Our legacy data indicates that caprines were probably the main asset of animal economy, and they account for more than 80% of meat supply at a few late Bronze Age sites, such as Episcopi Bambula, but also Flamudi Vunari and Melissa. In parallel, there was an increase in the cultivation of cereals, and this time period is distinguished by the transition from gloom wet to free threshing wet. We have evidence from Mapale, Castro, Ala Sultanteke, Calopsidia, and Apliki Karamallos. This change is consistent with the general transformation of the settlement pattern that consisted of an abandonment of many of the Middle Bronze Age sites located along the sedimentary river valleys on the island, and the establishment of new sites in the more fertile coastal regions. Free threshing wet requires watered fields with nitrogen soils, whereas gloom wet thrives in unirrigated soils and generally is sufficiently drought resistant. As free threshing wet doesn't possess greater nutrient ratios, we can hypothesize that this change was dictated by the greater ease of processing, but also by cultural reasons, including the availability of those storage facilities that generally characterize the centralized organization of late Bronze Age polities. In this regard, it's interesting to know that centralized economy probably dealt not only with the collection and distribution of staple commodities, but also with the phase of cultivation. And again, in this perspective, the increase in the amount of cash crops fits in well with this social political scenario. It's now the turn of paleoclimatic proxies, which can add a new variable, past climate, to our story. The state of paleoclimatic research and data from Cyprus was very frustrating until a few years ago, and we were left to depend on proxies from neighboring areas. The primary paleoclimatic proxies from the Levantine and Anatolia that are pertinent to the chronological period of my lecture today are shown on this map. Each one of these graphs has again the time in years pp on the x-axis and the z-score based on the 18th isotope of oxygen on the y-axis. Oxygen 18 is one of the environmental isotopes together with nitrogen 15, carbon 13, carbon 14, isotopes of uranium and strontium. Basically, the isotope ratios in the different samples, sediments, speleothems, biological shells, are affected by temperature, salinity, and precipitation, and we can measure their change from standard isotope measurements. In particular, oxygen 18 relates with temperature because its incorporation into water molecules is strongly temperature dependent. Higher temperatures implies more incorporation of oxygen 18 and vice versa. All the proxies from the Eastern Mediterranean region point to multiple episodes of rapid climate change, which are usually known as bond events, and they are marked on this graph by the dotted vertical lines. However, new pollen cores have been sampled in Cyprus over the last 10 years, and this creates a useful dataset for comprehending the magnitude and character of these events on the island. Currently, the legacy collection of Cypriot proxies consists of 2 cores from the Salt Lake of Larnaca, 2 cores from the Troodos, Almiro Livado and Passa Livadi, and 6 cores from the peninsula of Akrotiri. 2 of them have been analyzed and published. This dataset is very good to make a few assumptions based on the coastal regions and the Troodos Mountains, but more datasets are required to model the complex environment and topography of the island. So let's start from the mountains. This is the infer vegetational pattern from one of the Troodos cores, the one from Almiro Rivado, which covers almost completely the time period we have previously discussed in terms of population patterns and subsistence economy. On the left here, you have the result of archaeodemographic modeling from the Troodos region and from the entire island. The author of this study, Arethi Christodoulou, classified the various taxa into categories that can hide in finding patterns in trees and shrubs, herbaceous plants, and pterophytes, ferns and related plants, which provide crucial information about humidity. I won't go into great detail about what happened across the Troodos during the Holocene, but there's a few interesting points. The first point is the Aceramic Neolithic, where the vegetational pattern indicates a predominance of Graminaceae and generally low forest coverage in this region. As you can see, the quantity of charcoal, which is this line in the graph, the quantity of charcoal indicates regular or large-scale fires. Obviously, we cannot directly link these fires to human activity, but it's interesting to remember that 2 later ceramic Neolithic sites have been found in the middle of the Troodos woodlands at Kakopetrias Aios Nikolaos Tistegis and Kandra Aios Kyriakos. And this makes us wonder and then consider the very early occupation of the mountainous regions. The high quantity of Cyperaceae, which usually indicates humidity, coupled with the low forest coverage, might be the legacy of the moist conditions related with the so-called 10.3 kbp event. The amount of forest and the variety of pollen taxa increases during the ceramic Neolithic. The pattern shows 2 episodes, these 2, of decreased pine abundance along with the rise in Cyperaceae. Pino-Jupiter rates, which are typically regarded as complementary taxa in forest environments when juniper grows pine declines oscillate on a regular basis during the Chalcolithic period, and this coincides with three major fire events. An over decline in pollen counts indicative of woodland and forest coverage characterizes this period. This suggests that the climate was especially drying during this time, the long 4th millennium BCE again. And this is particularly evident in the pattern of oak at around 5 kbp, 4.5 kbp. The amount of pine pollens and all other taxa suggesting woodland coverage decreases in accordance with the so-called 4.2 kbp event. And this pattern continues until 3.7 kbp. This overall decline in the forest coverage, which also shows a significant rise in the, this overall decline in the forest coverage occurred during a time of rapid population growth, which also shows a significant rise in the importance of metallurgy. This probably indicates that deforestation and human impact are likely to blame for the noticeable decline in trees and shrubs up in the Troodos. At the very beginning of the Iron Age, the global climatic conditions were generally drier than before, and according to Finney, Dussar, and others, agricultural activities probably decreased for a few decades, enabling woodland areas to expand. This is precisely what we can make out from the amount of Pinus pollen. And here you see the peak at the very beginning of the Iron Age. It's important to keep in mind, however, that a potential decline in the size of cultivated areas at the end of the Late Bronze Age may also have been caused by a general decline in population and thus a reduction in the size of the cultivated areas. During the classical and Hellenistic periods, the vegetational scenario is dominated by woodland coverage, and the general pattern is quite identical to that of today. It's noteworthy that neither pollen core from Armillo Vadi nor Pasali Vadi contains any evidence of the extensive deforestation attributed to the Ottoman period, despite the fact that other historical sources argue for excessive animal herding and intensive agricultural activity. The taxa belonging to cultivated species or species associated with animal herding are in too tiny a quantity to be significant in the pollen diagrams from the Troodos, and thus there's no clear direct indication of intensive farming and herding practices. But we have some interesting insights from the pollen cores from Akrotiri and Larnaca. One of the two cores from Akrotiri, for example, offers a very clear picture of the climatic conditions along the southern coast of Cyprus from the late Chalcolithic to the historical period, and in particular, a direct understanding of the 4.2 kbp event and the end of the Late Bronze Age. This graph indicates the development of wetland, marshes, and bog, dry steppe, and other land coverage types during this period. First of all, the 4.2 kbp event, which is contemporaneous somehow with the Filia early Bronze Age transition. As you can see, the pollen record shows a significant decline in wetland taxa, this kind of petrol green area, as well as fen trees and riverine forest taxa that are almost absent between 4.4 and 4.2 kbp. At the same time, there is a peak in dry steppe taxa. After this very arid event, which impacted the site of Cyprus as well as the Troodos, we have the increase in the quantity of pine pollens from the Almiro Livado. The second one, we have 2 centuries dominated by wetland marsh and bog, excluding 2 intervals at 3.3 and 3.2 kbp. The first one is characterized by an increase in dry steppe, the yellowish pattern, and the second one by an increase of Mediterranean woodland, the kind of greenish brown pattern. These two intervals probably indicate that the end of the late Bronze Age in Cyprus were preceded by a gradually deteriorating cold and arid climate from approximately 3.5 to 3.3 kbp, followed by a cold and wet interval that other proxies from the Eastern Mediterranean place between 3.1 and 2.9 kbp. The core indicates also another change in Mediterranean woodland abundance during the Iron Age and 1.35 kbp, followed by a peak in wetland marsh and bog taxa at about 850 bp. The vegetational profiling correspondence of the 3.2 kbp event indicates decreasing water availability and a more restricted marsh environment. In addition, other identified taxa, not shown on this graph, also indicate a decline in the evidence for agricultural activity. Cerealia, for example, disappear from the profile of the other core that was sampled in Akrotiri. And this ties in nicely with the pattern found at Armiro Livado, where a rise in the variety of trees and shrub taxas at the end of the Late Bronze Age, early Iron Age, indicates an expansion of the forest in the formerly cultivated areas. Also, the Salt Lake core, here we are, shows the same pattern, which suggests a potential decline in agricultural activities with a sudden drop in the amount of cerealia and a rise in the taxa of the dry steppe, such as Artemisia and Asteraceae at 4.2 kbp. A similar pattern is recorded also at 3.2 kbp, where the decrease of cerealia is even more significant. According to the data from Hala Sultan Tekke, this period was probably characterized by a 40 millimeters per year drop in winter rainfall. The population pattern based on archaeodemographic proxies and what we deduce from the paleoclimatic proxies of Cyprus, including the Troodos and the southern coast, are very consistent. We can see that the end of the Late Bronze Age was marked by a population decline and most likely a steadily deteriorating climate, especially in the southeast, the Mesoauria, and probably also in the north. Although we lack direct evidence from the north, some proxies from Anatolia suggest that the climate became drier also farther north. The rise in the numbers of forest taxa during the early Iron Age provides also direct evidence for these processes in the Troodos regions. Although our legacy data are scattered and insufficient, the demographic pattern does not show any significant demographic decline during the transition from the Late Bronze Age to the early Iron Age. What affected the southwest of the island, where we don't have any demographic decrease as a result of these climatic conditions, is something we cannot fully understand in this moment. We lack local paleoclimatic proxies, but population modeling suggests that this region didn't experience a significant decline in human settlement. So this is the story, an early and incomplete story of the island of Cyprus during the Holocene. And these stories tries to integrate the global narrative that the CLASS project here in Durham is doing for exploring the broader region, Southwestern Asia, including Mesopotamia, Anatolia, the Levant, and the Arabian Peninsula. The proxy data we have now at our disposal helps us to start understanding how human cultures interacted with their environment over the Holocene period, but new proxies are required to deepen our graphs of the regional trajectories of Cyprus. What we can infer is that the history of human interaction in ancient Cyprus in the face of climate change is marked by a deliberate insular identity even from its formative periods, made up of a distinctive combination of vulnerability, resilience, and capacity for transformational adaptation. Thank you.
Thank you very much, Francesca, for this amazing combination of material and the tour de force of data. This was an excellent combination of so much information, and I'm sure there will be a number of questions or comments. Certainly, I have some questions.